Learn the mathematical foundations of recommender systems used in modern e-commerce platforms. Recommender systems create intelligent connections between users and products by analyzing patterns in purchasing and browsing behavior. Let's start by understanding what recommender systems are and why they're crucial for e-commerce. A recommender system is a sophisticated algorithm that predicts which products a user might like based on various data points. The primary goal is to maximize user engagement, increase sales, and improve customer satisfaction through personalized recommendations. The system takes user data as input, processes it through machine learning algorithms, and outputs personalized product recommendations. There are three main types of recommender systems, each with unique approaches and mathematical foundations. Collaborative filtering analyzes patterns in how users interact with items, finding similarities between users or items. Content-based filtering recommends items similar to what the user has liked before, based on product features and attributes. Hybrid systems combine collaborative and content-based methods to leverage the strengths of both approaches. Here are the three main types visualized: collaborative filtering, content-based filtering, and hybrid approaches. The foundation of recommender systems is the user item rating matrix, which captures all interactions. The rating matrix R has M users as rows and N items as columns, where each entry Rij represents user I's rating for item J. Each entry in the matrix can represent a rating, a purchase, a click, or any other form of user-item interaction. Here's an example rating matrix, where known ratings are shown as numbers and missing ratings are shown as question marks that we need to predict. Let's dive deep into the mathematical foundations of collaborative filtering, the most popular approach. Collaborative filtering has two main approaches: user-based, which finds similar users, and item-based, which finds similar items. For user-based collaborative filtering, we predict rating R_UI as the user's average rating plus a weighted average of similar users, deviations from their means. Computing similarity between users or items is crucial, and we have several mathematical approaches. Cosine similarity measures the angle between two rating vectors, ranging from -1 to +1. The cosine similarity formula divides the dot product of rating vectors by the product of their magnitudes. Pearson correlation measures the linear relationship between two users' ratings, accounting for rating scale differences. Pearson correlation uses mean-centered ratings to compute correlation, making it robust to different rating scales. This scatter plot shows highly correlated ratings between two users, indicating high similarity and strong predictive power. Matrix factorization is a powerful technique that decomposes the rating matrix into lower-dimensional latent factor matrices. We approximate the rating matrix R by multiplying two lower-dimensional matrices P and Q transpose, where K is much smaller than M and N. Matrix P represents user features in latent space, while matrix Q represents item features in the same latent space. Visually, we decompose the large rating matrix R into two smaller matrices, P and Q, that capture latent features. To find optimal matrices P and Q, we minimize the prediction error using advanced optimization techniques. We minimize the sum of squared errors between actual and predicted ratings, plus a regularization term to prevent overfitting. The lambda parameter controls regularization strength, balancing between fitting the training data and generalizing to new data. We use gradient descent to iteratively update the matrices P and Q to minimize our loss function. The update rule for user features is PU gets updated by adding alpha times the error times item features minus lambda times PU. Similarly, item features QI get updated by adding alpha times the error times user features minus lambda times QI, where EUI is the prediction error, calculated as the actual rating minus the predicted rating. Alpha is the learning rate that controls how large each update step is during the optimization process. SVD is a classical matrix factorization technique that provides an exact mathematical decomposition. SVD decomposes matrix R into three matrices: U containing left singular vectors, sigma containing singular values, and V transpose containing right singular vectors. The sigma matrix is diagonal, containing singular values in descending order of importance. By keeping only the top k singular values and their corresponding vectors, we achieve dimensionality reduction while preserving the most important information. Content-based filtering uses item features to find similar items and make recommendations. Each item is represented as a feature vector capturing attributes like category, price, brand, color, and other product characteristics. Item I is represented as a d-dimensional feature vector VI with features F1 through FD. We build a user profile by aggregating the features of items the user has previously liked or purchased. The user profile is calculated as a weighted average of item feature vectors, weighted by the user's ratings. We score an item for a user by taking the dot product of the user profile and item feature vector. For text-based features like product descriptions, we use TF-IDF to convert text into numerical vectors. Term frequency measures how often term T appears in document D, normalized by the total number of terms in the document. Inverse document frequency measures how rare a term is across all documents, giving higher weight to distinctive terms. TF-IDF combines both measures, giving high scores to terms that are frequent in a document, but rare overall. We need robust evaluation metrics to measure how well our recommender system performs. Mean absolute error measures the average absolute difference between predicted and actual ratings. MAE is computed by summing absolute errors over all test ratings and dividing by the number of test cases. RMSE is similar, but squares the errors first, giving more weight to larger prediction mistakes. RMSE is the square root of the mean squared error, maintaining the same scale as the original ratings. For e-commerce, ranking quality matters more than exact rating prediction accuracy. Precision at K measures what fraction of the top K recommended items are actually relevant to the user. Precision at K equals the number of relevant items in top K divided by K. Recall at K measures what fraction of all relevant items are included in the top K recommendations. Recall at K equals the number of relevant items in top K divided by the total number of relevant items. The cold start problem is a major challenge when dealing with new users or items with no interaction history. For new users, we have no rating history, making collaborative filtering impossible initially. New items haven't been rated by anyone yet, so we can't leverage collaborative signals. The solution is using hybrid approaches that combine content-based features with collaborative filtering, plus strategies like popularity-based recommendations for new users. Modern systems use neural networks to learn complex, nonlinear patterns in user-item interactions. Neural collaborative filtering models the rating as a neural network function, f of user embedding pu, and item embedding qi with parameters theta. Neural networks can capture complex, nonlinear relationships between users and items that traditional methods miss. A neural collaborative filtering architecture with input embeddings, multiple hidden layers, and a final output predicting the rating. Let's summarize the fundamental concepts and mathematics of recommender systems for e-commerce. Collaborative filtering leverages the wisdom of crowds by finding patterns in how users interact with items. Matrix factorization is a cornerstone technique that decomposes a rating matrix into user and item latent factors. Content-based filtering uses item features and attributes to find similar products and make recommendations. We optimize our models by minimizing prediction error using gradient descent and regularization techniques. Hybrid systems combining multiple approaches solve challenges like cold start while improving overall recommendation quality. These mathematical principles and algorithms power the recommendation engines of major e-commerce platforms like Amazon and Alibaba.